Good morning, Year 12s. Today we're looking at plotting trend lines. So, last video we looked at scatter plots and how to measure correlation. Today we're going to look at plotting a line through a scatter plot. Now, we want to fit the perfect trend line. Fitting the perfect trend line is very hard to do by hand. If you draw it on, everyone might draw a slightly different line. So, our calculators have a very nifty way of making sure they have the perfect line that goes through the points. And it's called least squares regression. It's regression that minimizes the square of the residuals. What I mean by that is, if you see each of these points on this scatter plot, that's point number 3, point number 2, point number 1, you see if we draw a line through all of them, we're going to miss it. Now each time we miss by a certain amount, this distance here to here, that miss is called a residual. It's the bit that we haven't covered. So it's a bit left over, hence the term residual. If we're exactly on the line, there is no residual. But you can see how each of these misses slightly. So this one misses above, below, etc. Now what our calculator does is our calculator essentially tries to draw different lines, like this, so that the residuals are minimized. However, because the residuals are occasionally negative, say this one here would be negative, trying to minimize negative numbers doesn't really make sense because you just try and get more and more negative numbers. So instead, what we do is we minimize the sum of squared residuals. We take each one of these residuals, say D1, and square it, D2, and square it, D3, and square it, and so on until we get the smallest amount possible. So what that looks like on our calculator is, if we have GDP versus infant mortality rate, we could insert document. Control I will get you insert. Data and statistics. GDP is the explanatory variable, infant mortality a response variable. If we decide to plot a line, add a movable line, we can actually move a line around. So we can try and do this by hand. And we can ask it to show the residual squares. What it's showing here is the equational line and the sum of squares. And you can see right now, it doesn't fit the points very well at all. My line is far too high. As I move it down, all those squared distances, or the residuals squared, reduce. And I can probably guess that the line will somewhere be about there. Now, see the residual of 39? That might not be the best we can do. So we go menu, I'm just going to remove that line. And you can make it do a regression. Ooh. And typically we're going to use the second one, a plus bx. Right. Now, my line wasn't far off that before, but let's see what the sum of squared residuals is here. (25). Alright, so my residual plot of 39 was really far too high. The calculator does this very quickly. That is what it's doing when it's finding the minimum sum of squares. Alright, now note for least squares regression to work, or the least squares line is a line that minimizes the sum of squared residuals. The assumptions are that the data is numerical, the association is linear, and that there are no clear outliers. Notice these are the same assumptions as those made for R. Alright. I've added instructions there on how to do a linear regression, should you feel the need to copy them into your books. And I do suggest you copy in instructions because you don't want to forget it. Alright, now there is a way to do this algebraically. Algebraically, we're after a line with the equation y equals a plus bx, where b is the slope and a is the y-intercept. Alright, now, if we have certain things, we can find the slope if we have r, sy, sx. R, we know from before, is the correlation coefficient. Sy is the standard deviation in the y variable, which will be the response. Sx is the standard deviation in the x variable, meaning the explanatory. Alright. Then, after we found the slope, we can then use the slope to find the intercept. So once we've got b, we can use b in here, where y bar equals mean of y and x bar equals mean of x. Alright, so an example of how you would do this is a study to find a relationship between the height of husbands and height of their wives has revealed the following details. Alright, mean height of husbands, mean height of wives, standard deviation height of husbands, standard deviation height of wives, correlation coefficient. And we can see that it's quite strong linear correlation. Generally, taller men date taller women. Just what it works out. Now, here, we're trying to figure out which is the explanatory variable, which is the response variable. The way the question's worded implies that men are here and wives are here. So, let's look at this here. If we want to find b first, we would use the equation for b and write it out saying b is equal to rsy over sx. B would be equal to r, which is 0.85, times sy. Now sy is the standard deviation of the y variable being the wives, so 4.8, over the standard deviation of the x variable, 5.3. And we calculate that. Give me 1 second to calculate that. Alright, so b is equal to 0.77, we'll go to 2 decimal places. And then, however, for the calculation for the next part, we would use the full value of b, which is 0.7698111. Alright, now to find a. A is equal to y bar take b x bar. Y bar take b x bar. So a is equal to, now y bar is the mean of the y values, which is the mean of the wives, so 169, minus b, which will be our 0.769811, times x bar, which is 180. And once again, give me a second to calculate it. 169 minus 0 is 155.14. So the equation of our line, when we put these together, is y equals 155.14 plus 0.77x. Now, if you write that, you don't get a mark, which is frustrating, and lots of people lose marks for it. The VCE is very strict on this. It doesn't want you to use x or y. It wants you to use the names of the variables. So here we would say wives' height is equal to 155.14 plus 0.77 times husband's height. Then you get the mark. Alright, thank you very much.